Hello and welcome. My name is Iqbal Singh Josan, and I'm going to present this webinar on antenna engineering part 2 of 2. This is a sequel to the previous webinar we had last Saturday, part 1. So I hope all of you have attended that, or if you don't have the need to attend that, you can still view the recording of that webinar on our website. Okay, let's now move on with this part 2. In part 2, these are the topics we are going to cover. We're going to talk about the antenna design and measurements process, and we'll also see how we can measure impedance, gain, and field patterns for any. And the two types of measurements involved in antennas is a near field and a far field, and how they're different from each other. And we'll also see how anechoic chamber and a compact range could be used for antenna measurements. Then we'll reflect a little on the RF site surveys. Before you install any wireless system, any antennas, even for a Wi-Fi or a cell site, site survey is necessary. Without that, you never begin. So we'll see what process we follow for that. And then we'll move on to the diversity techniques in antennas, diversities which are of different types. It could be of frequency, time, space, polarization, and pattern. And then we'll move on and see how we combine the different signals received from different antennas in a diversity scheme. So diversity combining. And after that, we move on to how we can add to the wireless system capacity. If we want to increase the number of users served by a typical wireless system, a typical cell tower or a Wi-Fi LAN, what are the different techniques we can use to add to the system capacity? And you might have heard of some of those techniques like frequency reuse, cell splitting, cell sectoring. Then we'll also talk about the advanced techniques used in LTE, the 4G ELT networks of flexible frequency reuse. After that, we'll move on to talk about base station and indoor and mobile handset antennas and how they're different from each other. And in particular, a technique used to enhance the performance of an antenna. It's called antenna tilt. And last but not the least, we'll talk about MIMO, or you call it MIMO, and it's the latest in the 4G wireless networks, and how we realize benefits from MIMO, a MIMO system, like antenna diversity, beam forming, and space division multiplexing. And finally, we'll talk about different applications of MIMO in most of the dominant wireless communication standards like Wi-Fi, WiMAX, and LTE. And where is this MIMO scheme leading us to? What's the feature of MIMO? Okay. So now, first of all, the antenna design and measurements. Now, before we move forward, let me tell that you can interact with me by writing a question on the left bottom of your screen, a chat box you see. You can just write a question anytime and you can interact with me. Okay. So let's have a recap of the antenna design parameters that we covered in the previous webinar of part 1. So all these parameters have to be considered whenever we design any antenna. So we have input impedance. We have to consider size, weight, and power of the antenna for a specific application. Then we have to consider the field and power patterns. What type of power patterns we want the antenna system to have. And then we want to know what is the half power beam width. What is the width of the beam that we want to generate with a transmitting or a receiving antenna. And what is the antenna gain we are targeting at? What type of coverage we want to have with that antenna. Directivity. So what type of directivity we want to have? Like we want to transmit the radio signal in one direction or multiple directions on an omnidirection, or what is the directivity? Then what is the return loss? Like can we afford any return loss or not at all? Like what type of impedance matching we must have? Effective aperture, what type of aperture or collection area of the signal for an antenna? Polarization, is it vertically polarized or horizontally polarized or circularly polarized? It again depends on the application we want to design the antenna for. And then the axial ratio, and of course the very important one, the ERP or the EIRP, effectively radiated power. So this tells you what amount of power you want to radiate with your antenna. And finally, we have the bandwidth. What is it, a narrow band antenna or a wide band antenna, or whatever of bandwidth we want to have? So considering all these parameters, so what are the different techniques we can use? Now, before that, let's see that we need to follow a process to design any antenna system. So the process begins with the RF system design and analysis. which lists out, okay, antenna is one important component of this RF system. And what are the requirements? So we define the antenna requirements to begin with. So this will specify the gain, directivity, the ERP, and all those other parameters that we considered in the previous slide. So after that, we proceed to find a solution for the design of the antenna, for the actual physical design of the antenna. And there is a decision box here that do we have a closed form solution? A closed form solution means we may find a set of equations into which we input our desired parameters, and the result of that equation gives us the physical dimensions of the antenna. Now this could be possible for very simple designs, like a half-wave dipole. Well, like if you know the wavelength, and it's very easy to calculate the length of the element, and you could always find easily available information on that to design that type of antenna. Now, if there is a closed form solution available, we just make a draft antenna design. So draft antenna design is first the design on paper or on your computer by using one of the CAD tools. So after that, we can again decide that do we really want to fabricate this antenna? Like if the cost of fabrication is not too high, we may even fabricate the antenna and then test its performance. And if it meets our requirements, then the antenna design is final. Otherwise, we may have to rebuild the antenna. Now there can be situations where rebuilding an antenna could be very expensive. Like you cannot rebuild a cell tower. Like it will cost you a lot of money. So in such cases, we may want to simulate performance. Simulate performance by using some available software. And if with those parameters, does our antenna perform to the desired requirements or not? If yes, then the antenna design is finalized. Now there can be situations in complex design of antenna systems where the closed form solution may not be available. So if the answer is no, we use numerical solution techniques, which are advanced techniques, and there we use some readily available software from some vendors, and it might use one of these methods: finite element methods, finite difference time domain method, method of moments, or physical optics method. One of these methods the software might use to build a draft design for you. Now after that, again, we decide if we fabricate antenna, yes or no, based on cost analysis. We simulate performance if we cannot build the antenna at this point, and if it meets requirements, we finalize the design and then we build the antenna. So this process we can follow for any antenna, small, big, or for any application. These are the general guidelines. Okay, so now let's move on to the next one. Now here we have one important equipment that is used by the antenna designers, the vector network analyzer, which can be used to experimentally measure the impedance, gain, or field patterns of an antenna system. We could use them to measure in the electrical plane or the horizontal plane, the E plane or the magnetic plane. So how do we do that? So impedance measurement, the VNAs, the vector network analyzers, typically use the principle of two-port networks. So two ports, you need to connect two antennas, a transmit antenna and a receive antenna. These two antennas may be of same type or of different type, but essentially you are building a circuit out of it. So once you have two antennas and two ports, each having impedance of 50 ohms, you complete the circuit. And then it is possible by using the properties of that electrical circuit to measure the impedance at each port. Now this is how we do it. Here you see the mathematical representation of a two-port network, which essentially what it does, it measures the ratio of the reflected and the incident voltage on each port. So these are the equations. These are very standard equations in any electromagnetic textbook you can find. So it's pretty straightforward. So the VNA, what it does, it measures the reflected and incident voltage at each port to build a scattering matrix, and use this scattering matrix to calculate the input impedance at each port and even the mutual impedance. So and in this slide, you can see the formulas that we can use to determine the impedance from S parameters or scattering parameters. So Z11 is the self-impedance of port 1 where the transmit antenna is connected, and Z22 is the self-impedance of port 2 where the receive antenna is connected, and Z12 is the mutual impedance. So if you have the vector network analyzer and the circuit setup with transmit and receive antennas, it's very straightforward. straightforward to measure the impedance. Now, let's go to see what are little more advanced techniques which is for antenna measurements. So typically, we use a far field or open area test site where we set up a transmit antenna which has a position controller and a VNA setup, and our antenna under test is in the line of sight of that antenna at a distance. Because here, our focus is we want to measure its gain and field patterns and at a far field. Remember from the previous webinar that a far field is important for us. It's a far field that we use in wireless communication, and the parameters are very important. So the antenna under test again has a position controller, and we can move the height of antenna up and below, left and right, using the position controller. And of course, the limitations are that we must have an open area test site available which doesn't have any EMI interference around. Like you cannot have a power transformer nearby where you're doing this measurement. So, but it's a very common technique which has been used since the beginning. Now then, sometimes it may not be practical to have an open area test site. This is typically true when the size of antenna is very big or the size of antenna is very small. So in that case, it is possible, or there are techniques to do that with an indoor anechoic chamber. So it's a very large room actually, which has electromagnetic shield around all the walls and the roof and the floor of the room, and you have electromagnetic absorbent material, as you see in the picture here, that is used to shield any EMI coming from outside or even to avoid any reflections from inside. So inside the anechoic chamber, we erect the transmit antenna and the antenna under test, and then connect these two antennas to a vector network analyzer, and pretty much use the same process we use in the open area test site. The difference is now we have a indoor anechoic chamber where we can use the far field measurements inside the chamber by using these electromagnetic shield around the room, and by avoiding any reflections from the walls and the roof and the floor. Okay. Sometimes it may be practical to have. Okay, before I move further, this is just a picture of the electromagnetic absorbent material that you see on the walls of anechoic chamber. This is one type of them, which is used to avoid reflections, but there could be different types too. If you search online on the web, you will find many different types. So idea is to avoid reflections from the walls when we're doing far field measurements in the anechoic chamber. Okay, so now, okay, why is it conical? There's a question that why is it conical? This helps avoid reflection. If it reflects, it will not come back to you. It will go inside, reflect to the another cone, and then to the other cone. So this minimizes reflections. That is why it is conical. This is the most common shape used, and they are usually metallic because metal will reflect it. Okay. Now there is another variation of this anechoic chamber called indoor compact range, where it's not a very large room. It's a relatively smaller chamber, smaller room, and where you basically use a reflector to transform the beam coming from a horn transmit antenna and make it a plane wave, and then you see the antenna under test mounted in front of the plane wave coming off from the reflector. But pretty much the principle is the same. You have this electromagnetic shield, and you avoid reflections, and it's possible to make measurements using even a compact range. Okay, now let's move to the next one. What we have here. So now, far field measurements. Let's say what procedure is recommended to be followed when we are doing far field measurements, whether using open area test site or an indoor anechoic chamber or an indoor compact range. So this is how we'll do it. So first of all, we'll calibrate the range and equipment for far field test setup. We use standard gain horn antennas as the receiver for calibration. So before we even mount the antenna under test, we just put a known horn antenna whose standard gain and field pattern is known, and just calibrate our system, our test setup. And once we have done that, then it provides you a good reference. Then you replace your standard antenna with the antenna under test and do all the measurements by moving the AUT in azimuth and elevation planes, and you measure and record magnitude and phase of the received signal at different positions of azimuth and elevation. And then, of course, you don't have to calculate anything manually. Now you have measurement and control software that will do it for you. It will take in the measurements and build a field pattern for you. Okay, let's move on to the next slide. Now, next topic is the near field measurements. So near field measurements these can also be important because these are required in certain applications where you have to mount your antenna with other equipment nearby. So you need to know how does the near field looks like, so it doesn't interfere with any other stuff which is mounted around it. So and another option is that here is not very expensive technique, because here you from the near field measurements you can calculate far field radiation pattern. That is also possible. You use certain techniques like aperture integration, geometrical theory of diffraction, and fast Fourier transforms can be used to take in the near field measurements and build a far field radiation pattern out of it. Of course, there will be a limitation there. You can because it's a mathematical model you are using here, so there will be slight variation from the actual one, but it's practically useful. So of course, it will have a limited range. You can do it for a limited range only. You cannot do it for an antenna which needs like 100 miles coverage. Okay, that may not be possible. But for limited range, like for a Wi-Fi antenna or for maybe a small cell antenna or even a cell site antenna, it may be possible. So considering this, talking about this, let's move forward. That how we. Well, there is a question. Yeah, with Veda Prabhu is asking that earlier I said that one should not measure in near field in earlier lecture. Yeah, that is true. That is very true. When we do measurements, but this is a special way of measuring. This is one way of measurements which can be used to derive far field measurements too. Normally we don't do that. You know, in commercial deployments we don't do that. But still there is an alternate technique available which has been devised to overcome the limitations of the open area test range or anechoic chamber, because they are expensive set of equipments too. So if you have the software available that computes from near field to far field, you could use that technique too. It's available. Yeah, but in general, we will not use a near field measurement. It's not recommended to do measurement in the near field unless you have the conversion software available, which will convert these measurements into the far field pattern. Okay. So now, when you measure in the near field, you could do it different ways. One way is that you compute the near field planar surface coordinates. So in this case, the antenna under test is stationary, but the probe that moves along X and Y axis, and we can make measurements in the near field. Okay? So you have different points where you measure these, the gain and feed pattern, and to feed into your software that will convert this into the far field radiation pattern. This is one way of doing it. You compute a near field planar surface. Other way you could do it is the plane polar surface, where you have an angle. Where what happens, your antenna under test rotates around z-axis, and your probe moves along y-axis. So you have r and phi coordinates which can be used. So these two techniques, they are good for high gain antennas, where you have a high gain involved. Then they are very useful to compute the near field for a high gain antenna. Okay. So another surface you could use to measure the near field is a near field cylindrical surface. So here the probe moves along z-axis and rotates around z-axis, and you get this r, phi, and z coordinates. This is again very useful for high gain antennas. Okay, just give me a second. I think I skipped one slide. Okay, so now let's move on to the RF site surveys. For an indoor wireless network, RF site surveys are very important before we install any RF equipment. So for indoor wireless network, this is a process, I think some of you might be familiar with this who are working in the field. So, but for the sake of completeness, I will just go through the simple steps. So first of all, we need to have a facility diagram or a floor plan of the building. We walk through the building and perform a visual inspection to just have a look that where we need to position our access points based on user areas. Where is the user sitting on the desks, and so that we can optimize our coverage of the area. Then we install access points at identified locations for preliminary signal strength measurements in user areas. And if we log signal strength at certain data points and any measured sources of EMI. Now, if we need to keep our antennas away from the sources of electromagnetic interference, or do relevant adjustments that need to be done. Then we analyze these measurements and adjust the location of access points to maximize our signal to interference and noise ratio. Okay, so for outdoor surveys, outdoor wireless networks, where you have a cell tower involved, its procedure is basically the same, but there are certain differences. So because there you have a terrain involved. You have to get the terrain maps for the coverage area of the cell site, whether it is a flat area where you have hills and mountains or undulating site. So you just have to perform a drive test for signal strength measurements in the coverage area. Now here it's a little tricky here because once you erect a cell tower, after that it's very hard or costly or expensive to relocate the cell tower. So it has to be done very carefully. You have to really drive around the area and see what is the best site for installation of the cell tower. And once it is installed for measurement of signal, again, you have to do a drive test to make all the measurements, identify any potential landmarks and buildings that could block user areas, log the signal strength measurements and any measured sources of EMI, analyze those measurements and make recommendations to maximize signal to interference and noise ratio in underserved user areas. Okay. So very, very straightforward topic, but idea is that we need to be very, very careful about the site surveys. It must be done before installing any antenna system. Now moving on to the topic on diversity techniques. So before we do that, let's understand a little about the multipath propagation. So let's consider a mobile receiver, a cell phone, which receives 3 signals from the cell tower. One is the path 3, which is a direct line of sight signal. Other is reflected from a building, which is path 2. And the third one is path 1, which is reflected from a hilltop. So any mobile phone or cell receiver will receive multiple signals transmitted over multiple paths. Now what happens? These signals could add each other destructively or constructively. So if any two signals received by the cell phone or your mobile receiver, they are out of phase, means they are 180 degree out of phase. They will cancel out each other and you will see no signal. But if they could arrive in phase 2, like both signals exactly overlapping each other, then that will boost the signal strength. But in reality, what happens? The user is moving around with the cell phone, and the end result would be that they will not completely cancel out and they will not completely boost the signal. It will be somewhere in between. But it would definitely cause a 20 to 30 dB fading. That is the major fading in the signal that happens due to the addition and subtraction of these different signals which are received by a cell phone or a mobile receiver from different paths. So this is called multipath propagation, and it's really a challenge to deal with in wireless communication. One is that it causes fading, and other problem we have is of the inter-symbol interference. So if we have digital transmission, now we have digital wireless communication everywhere with our 2G, 3G, and 4G networks. So what happens? Because there is a time delay involved on these multiple paths, so the symbols will overlap each other. Like in the picture you see, path 1, path 2, path 3, they are delayed signals, delayed with respect to each other. And at one point, the symbol 1 and symbol 2 on path 2. On path 2, you have symbol 1, it overlaps with symbol 2 from path 3. So what happens? Your data signals or data bits which are being transmitted using these different paths, they will overlap each other and what will happen? That will cause a corruption of data bits. Your data will be corrupted. And in our terms, we call it inter-symbol interference. The symbols interfere with each other. So that means if you transmit some text, it might be garbled as the end result. Having considered that, now let us see how we can use diversity techniques to mitigate the effects of fading that we have just seen. So there are 5 different techniques that can be used: frequency diversity, space or receive diversity, time diversity, polarization diversity, pattern, or it's also called angle or transmit diversity. Now we'll see in detail how all these different techniques can be used to mitigate the effects of fading and inter-symbol interference. Okay. Now, frequency diversity, it involves summation of same information with different RF carriers that fade independently. Okay. So what we do actually, we get we double the spectrum. There is F1 frequency and there is an F2. And we transmit two signals at two different frequencies. It's a copy of the same signal transmitted on two frequencies. So in the picture you see transmitter 1 and transmitter 2. Transmitter 1 tuned to frequency 1 and transmitter 2 at frequency 2. Same way on the receive side we have receiver 1 on frequency 1 and receiver 2 on frequency 2. Now the assumption here is, and it's a fact actually, the major fact, that if the frequencies, the two frequencies are at least 2 to 5% far apart, then they will not fade at the same time. They will not fade, they will fade independently, in other words. If they fade independently, we can use this inbuilt redundancy in multiple frequencies to achieve frequency diversity. Like if you lose signal from one frequency, you can retrieve it from the other one. Or if you lose from the second one, you can retrieve from the first one. So this is called frequency diversity. Simultaneous transmission of same information with different RF carriers that fade independently. Now, just note this point, fading of independently is very important. If they don't fade independently, then you don't achieve diversity. And to achieve that, there must be 2 to 5% separation between frequencies. Okay. Okay, now let us see what are the pros and cons of having this type of diversity. Now pros, of course, you have very high path reliability and you have full and simple equipment redundancy. You have two of each equipment. You have two transmitters, two receivers, and two of everything. There's a single antenna but two frequencies, and it's considered to be a wideband antenna on both sides. Okay, so that is a pro. But it comes at a cost. It becomes more complex, more expensive, and more spectrum is required. Spectrum is expensive these days, so it adds to the overall cost of the system. But sometimes, okay, where there's no other means available for diversity and we must have 100% reliability, it may be used. Okay. So having considered frequency diversity, now let's move on to the next one, the space or receive diversity. Now here we have multiple antennas which are used to receive independently fading signals. This is similar to in the multipath propagation we have seen. We have multiple signals coming from different paths. So we could have multiple antennas on the receive side to exploit the independent fading of these signals. Now remember here, they are independently fading because they are following different paths. From the transmitter, we have only a single transmitter, but signal one, there's one path 1 and there's a path 2. And if we keep a separation between two receive antennas more than like 100 of wavelength, it's possible to achieve spatial separation in this case. Now in the next slide, you see a formula here for antenna separation. It's a classical formula which could be used when designing such a system for a space or receive diversity. Well, there's a question, isn't the vertical separation actually half wavelength? Well, the half wavelength applies in a different situation. That means the minimum length between two antennas cannot be less than half wavelength. But definitely you can have more than half wavelength. Okay, so definitely it's more than half wavelength. We are keeping it 100 times of wavelength. So that's entirely different thing. Half wavelength means the two antennas cannot be closer than half wavelength, but they can be far apart. The distance must be greater than half wavelength. So here you see the vertical separation, we are keeping 100 times of lambda. And of course, they cannot be very close. They cannot be closer than half wavelength, but they can be wide apart. Here we are keeping them wide apart so that the signals received can be independently received from two antennas to achieve space or receive diversity. Okay, let's move on to the next diversity technique that we have here, time diversity. Now this is also an interesting one. Transmitting packets multiple times and each transmission separated from the next by time t. Time t is the time between two consecutive transmissions. Now how do we determine what is this time interval between two repeat transmissions? You know, the idea seems very simple, like you just transmit the packet again, and if you lose the first one, you will receive the second one. But again, here we have to consider the two signals must be independently fading. So the fading can happen over a period of time too. So there is a coherence time. There is a definition called of a time of the channel called coherence time of the channel, which is represented by tau. So coherence time is the time over which a channel impulse response is constant. You know, because of this fading, environmental fading, No, like the fading can happen not just because of reflection or multiple signals received, but the channel parameters can also change. If it is a rainy day, you will have a different channel response. If it is a sunny day, you will have a different channel response. Or from time to time, they can change. So we define a time, coherence time, which is defined as time. Always the channel, we know for sure that channel impulse response is constant. Now, if we know that time from actual practical measurements, then we know that our time t, it should be more than the coherence time. Then we can be sure that the two packet transmissions are actually independently fading. And if they are independently fading, we have achieved what we have achieved? Time diversity. So that is how you explain it. So after this time diversity, what we have polarization diversity. Now this is very straightforward. In the previous webinar, we have seen that we can have multiple polarizations and vertical and horizontal. The electric field, we can have a circularly polarized transmission where we have electrical field which is in the vertical EV component and an EH component. Now it is determined by measurements that, well, there's a question, is there correlation between diversity and impedance? Well, these are two independent parameters. Impedance, when you say impedance, you define the feed input impedance of an antenna. Okay. When it's diversity, we are talking about multiple antennas, and each antenna will have its own impedance. Okay. And if the same types of antennas, they will have same input impedance for each. And they are fed independent. They have independent feeds. So they are entirely two different parameters used in different contexts. Impedance is the ratio of voltage and current defined at a certain point on the antenna, but diversity means how you transmit multiple copies of a signal so that you achieve some redundancy or a backup in the system. I hope I have answered your question, but you can ask me again if more clarification is needed, or write me in email also. Okay. So in polarization diversity, there is very low correlation between horizontal and vertical polarizations, and they are unlikely or very low probability of them to fade simultaneously. Okay, so we are receiving two copies of the signal, one in the EV and one in the EH, and both of them are independently fading, so we achieve what? Polarization diversity. Okay, let's see what is next in diversity. Pattern, angle, or transmit diversity. So here we use multiple copies of a signal which is transmitted across space and time over multiple radio beams that fade independently. Again, here we have multiple paths, but we are using multiple transmit antennas, and you use space-time block codes which insert a time delay between each of these beams to achieve spatial isolation, and each of the beam fades independently, so we achieve pattern or transmit diversity in this case. This is the one which will actually move on to MIMO and MIMO. Okay, so Veda Prabhu has a question. What about polarization diversity in circular polarization? Well, when you do circular polarization, you are actually transmitting the same signal over over the vertical and the horizontal, right? Yeah. So in that case, what happens? The same principle applies actually. So in circular polarization, it's automatically achieved. If you lose the vertical component, you still have the horizontal component on the same signal, right? So it's a very good question you have asked. That polarization diversity by inherently is implemented in circular polarization. This we have seen in the previous webinar too. So the idea here was to highlight that fact over here. So we definitely have diversity inherently implemented in circular polarization. So our cellular systems, well, they could if they could implement circular polarization in their cell towers, then on the handset you could, if you lose the vertical component, but you still have the horizontal component, and your fading effects will be reduced. Very good. Okay. Yes, Veda Prabhu, I think do I have another question? Please type your question. Is it not clear? Yes, with circular polarization we do have. With circular polarization we do have a diversity. If you have. Okay, I'll move on. You can write me an email. You can write me an email if you need more clarification on this question. Thank you. Okay, now before we move on further, we have an interactive question. Number 1, which of the following statements are true? So let's see. Frequency diversity provides full equipment redundancy. Multiple transmit antennas are required in space diversity. A channel's impulse response is variable over coherence time period. Polarization diversity can be gainfully used for handheld terminals. For diversity schemes to work successfully, the multiple radio signals must fade independently. So please write the answer number in the chat box. Which one is correct? Which one you think is correct based on what we have covered so far? I'll give you some time to think about this. Let's review this. Well, frequency diversity provides full equipment redundancy. That is true. Multiple transmit antennas are required in space diversity. Well, that is actually not true, because in space diversity you have multiple receive antennas, not the transmit. It's not essential to have multiple transmit antennas. A channel's impulse response is variable. No, it is not variable. It has to be constant over a coherence time period. Polarization diversity can be gainfully used for handheld terminals. Yes, that is very true. For diversity schemes to work successfully, the multiple radio signals must fade independently. That's so many of you have answered the questions correctly. Thank you. Let's move on to the next one. Diversity combining. How do we combine these multiple signals from multiple antennas? Techniques to combine multiple redundant signals at the receiver. Now, these could be combined either based on what stage you are combining the signals. You could use pre-detection. That means combining of these signals happens at the IF stage or intermediate frequency stage before you extract the baseband signal. Or you could extract these signals at the post-detection point, where combining happens at the baseband stage. And then based on how we do the combining, there are 3 different types of diversity combiners: selection, equal gain, and maximal ratio. Let's talk a little more detail about all these subtopics. Diversity combining, pre-detection. Combining happens at IF stage. So it looks familiar, this picture. You have the input signal received. Signal 1 is received, signal 2 is received at the mixer, and with you mix it with the local oscillator frequency and you extract the intermediate frequency. So before you do the discrimination or you extract the baseband signal, you just combine the signals at the IF hybrid combiner. This is one technique. And other way is post-detection, where you actually retrieve the baseband signal. You see the signal 1 feeding into FM discriminator and signal 2 feeding into another FM discriminator. You have baseband signal 1 and baseband signal 2, and you combine the 2 outputs. This is how you combine. Now this again, there's no pros and cons right to one. The first one, second one. It depends entirely on your implementation. What makes sense to you in this particular application? Sometimes it may be more cost effective to do it one way or the other way. Okay. So let's move to the next one, selection combining. Now in this technique, what you receive these 3 different signals, and there is a switch on your receiver which receives the signal which has the maximum signal to noise ratio. You just select that one. Once it falls below a threshold, then you move on to the next one. So this is how you combine the 3 different signals traveling over 3 different paths. Okay, moving to the next one, equal gain combining. So this is an equal weighted summation of all signals in amplitude and phase. You just combine all the signals, and even if you lose one, you still have 2 remaining, or if you lose 2, you have 1 remaining, and your fading is dramatically reduced this way. Next way we could do it is the maximal ratio combining, where it's a weighted summation of received signals based on SNR. The strongest signal has more weight and the weakest has the least. So we provide some weight to the strongest signal. There could be a preferred path which is always available and sometimes it fades, but the other 2 paths may not be as reliable. So we increase the weight of the signal, like maybe the direct line of sight signal is more reliable at a certain point or location, then we give more weight to that signal and less to the other ones. So again, it could vary from the application to application, which technique you use to combine the signals. So now another important term that we need to understand in diversity gain is nothing but a relative increase in SNR due to diversity. Now imagine in this picture you had only one receive antenna. This is space diversity scheme. So here imagine you had only receiver 1 and you had signal to noise ratio 1, SNR 1, that you could achieve with one antenna. Now, if you have two receive antennas, RX2, the combination provides you with improved signal to noise ratio of CNR combo. So the ratio of CNR combo to SNR1, SNR combo to SNR1 is the diversity gain. I hope I clarified this. The ratio of signal to noise ratio, the relative increase in SNR that you achieve due to any diversity scheme. I have given the example of space diversity, but this formula applies to any diversity scheme. You simply see what is the increase, what is the benefit of for me to have a diversity scheme. Okay. Now let's move on to the next very interesting topic of system capacity and multiple access. The wireless system capacity is of concern to all the commercial carriers, all the commercial wireless communication carriers, as 2G, 3G, or 4G, because what happens, the frequency spectrum in any country is a scarce physical resource, and you need this to create multiple physical channels to serve multiple users in any geographical region. And you know, in every country, the governments basically auction this frequency spectrum, and there is a big cost involved in it for the carriers. So they are always under pressure to devise techniques how we can serve more users using the same frequency spectrum. So one very popular technique which has been used since beginning of this digital communications is the frequency reuse, where we reuse the frequency. We serve one set of users one frequency, and again we reuse it. Now in this case, the co-channel interference will be a limiting factor, as we'll see in detail, in little more detail in the next slide. Then we could split a cell into smaller cells to increase channels per unit area, and we could even sector the cell into angular sectors. Then the latest on the scene with the 4G wireless communication is small or femto cells. We could even reduce the size of a cell, reduce the area of area served by a cell to achieve more system capacity. Now let's see how we achieve that. Okay, so frequency reuse. So here we keep the cell size relatively small. It could cover an area of 4 to 8 miles. It will be served by a single base station. Typically, the height will be 50 to 300 feet with an ERP of 100 watts, which is very typical. It could be a little more or less than that number. Now, in this case, what we do, the adjacent cells have different sets of frequency channels, which allows reuse of frequency. Now, in the picture, you see there are 4 channel sets here, 1, 2, 3, 4. And if you look at any of these hexagons, each hexagon represents one cell area actually. It's surrounded by a different frequency. Like if you see the cell with the allocation 2, it is surrounded by 1, 4, 3, 1, 4, and 3. There is no 2 adjoining it. So adjacent cells have different frequencies. And if you see the number 2, after skipping one more cell area, then you have again number 2 assigned to a different cell area. So you are reusing frequency. You see, number 1, number 2, number 3, number 4, all are reused, but they are not lying in the adjacent cell. So now there are few parameters we need to consider here when we do frequency reuse. First of all, the number of frequency channel sets, or N, we call it N. So there are only certain numbers which can be used for regular repeat patterns, hexagonal patterns. Like you could use N equals 3, 4, 7, 9, 12, 13, and so on. Now this example is N equals 4, where we have the whole frequency spectrum available to us divided into 4 sets. And we repeat the frequency from 1, 2, 3, 4, and so on. Now there is a question. It's where FDMA enter in consideration, frequency division multiple access. Well, yes, this is an example of FDMA, but you know which time slot allocation. Now these things are not relevant at this point of time because we are only focusing on how we reuse frequencies. That time slot allocation of things will depend on what standard you use, whether you use a GSM, a CDMA, or if you are using FDMA at all, because in CDMA you don't use FDMA. So if you use GSM or in LTE, what type of time slots you're using. Those will be covered in future webinars when we cover in more detail about each protocol. But here our focus is that we are trying to reuse frequency spectrum in different cells, and how do we do that actually, okay, to avoid co-channel interference. Okay, so next slide. Now another important factor is the frequency reuse factor. FRF. This is the reciprocal of n. So if we have divided our frequency spectrum into 4 channel sets, so 1 by 4 is the frequency reuse factor. That means in one cell we are using only 1/4 of the spectrum available. We are dividing, let's say I have a spectrum of 100 megahertz available to me, which is allocated to me. I divide them into 25 megahertz of each. So each cell will have only 25 megahertz of bandwidth available to serve the users in that area. So n should be large or small. Well, very good question. Let's see in the next slide what happens if we make it n if we make n large or small. Definitely there are applications of that. Okay. We use distance ratio, Q. Now this is defined as the ratio of the co-channel cell spacing and the radius of the cell. Now you see in the picture you see that how we measure D. It's a co-channel cell spacing. What is the co-channel? So here number 1 is reused again after skipping one cell site. So the distance between the two cells we're using same frequency is called the co-channel cell spacing, and the radius of each cell is R. So reuse distance ratio is defined as a ratio of D and R, co-channel cell spacing and radius of cell. Now this is an interesting parameter. This will help us understand what happens if n is large or small. Okay, let's go to the next one. Okay, now this is the slide which the question somebody was asking a question that n should be large or small. So what happens if we make n very large? Let's say we have I have a frequency spectrum available which is 100 megahertz, and I make n equals 10. 10 means I have only 10 megahertz available in one cell. That means my capacity in one cell is reduced. I cannot serve as many users. Okay. So if n is very large, of course, the benefit I have is that the two cell sites will be far apart. There will be almost no co-channel interference. There will be no interference because the two cell sites are so far apart when the frequency repeats that there is no interference. But the downside is that I have reduced the bandwidth that is available in one cell site. I have only 1/10 of the bandwidth now. If I had used n equals 4, then I will have 25 megahertz. So I could have served more users in my cell site. So it's really a trade-off between capacity and quality. It depends on if I have to serve too many users in my cell site, then n has to be small. It cannot. I'll try to make it n equals 1. Like if I have all 100 megahertz available for me for one cell site, I can serve so many users. I can serve 4 times the number of users because I will have more number of physical channels available. But if n is very large, I have better quality, but at the cost of having to be able to serve less number of users. So we'll see in another slide that how in LTE we try to make n equals 1. So in general, it will be desirable if you see from a commercial point of view, you want to serve more users at an acceptable quality level. Like at acceptable quality level, again, it's a very relative definition. But the idea is to maximize your number of users. Then all these commercial carriers, they will try to make n equals 1 from a commercial point of view. But yeah, of course, the sacrifice, you may have some interference. And then how do you tackle that interference? Now, another important frequency reuse parameter is the carrier to interference ratio, CIR, or also known as signal to interference ratio. Now, this is the ratio of average received carrier power, which is you write it S or C, to average received co-channel interference. So suppose a user is within a cell site and he is receiving a direct signal from the base station. Now he might be receiving some signal from another base station which is running at the same frequency. So that is your interference. So how do we measure that? We measure the average received carrier power and the ratio of that to the average received co-channel interference power. This is very important parameter. Typically in actual practical measurements, we must keep a difference of 18 dB. Our received signal power from our home base station must be at least 18 dB higher than the received co-channel interference from a different base station which is running at the same frequency. And how do we achieve that? Okay. Now, one technique is cell splitting. Now, what the carriers will do, this has been used in 2G networks before. The congested cells which have more user population, like maybe in a downtown area or in a market area where we have so many mobile users, you divide the cell into smaller cells, each with its own base station. So is pretty much straightforward. But smaller cells need lower power transmitters and lower height antennas, thus permitting greater frequency reuse. So after cell splitting, what we can do? We can sector the cells into multiple sectors. Like you see, we could divide a cell into 3 sectors of 120 degree each, or 6 sectors of 60 degree each. Now this is very widely used in 3G networks as well as previously in 2G networks. If you see a cell tower, you will have a triangle. The antennas form a triangle actually. Why they form a triangle? They use 3 sectors of 120 degree each, and you have directional antennas. So each sector is served by a separate directional antenna, and each sector is allocated a separate frequency channel set. Now this provides you a lot of improvement over the co-channel interference. Why? Now let's consider if you had an omnidirectional antenna where you had no cell sectoring. That means the co-channel interference will enter from six sides around the antenna. We are presenting a cell with the shape of hexagon. Okay, so if you model it like that, then the interference can enter from all 6 sides, all around. But if you have directional antennas, let's say 3 antennas divided into sectors of 120 degree each, then for each antenna the interference can enter only from one side. So we have reduced the co-channel interference this way by providing 3 different directional antennas and dividing the cell into 3 sectors of 120 degree each. That is additional benefit. So this is the most widely deployed technique used in current 3G and 4G networks. How to reduce co-channel interference so that we can maximize system capacity, wireless system capacity. Okay, there's a question here, but making cells within cells drastically reduces the individual bandwidth, right? Well, yes, but you know, if you have 3 different frequencies, if you have 3 different frequencies, and if you achieve more, if you have higher bandwidth available, higher total bandwidth available, then it is possible to add system capacity. Making cells within cells, yeah, definitely. When you do that, you need more bandwidth. You need more total bandwidth actually, right? So you need a wider spectrum, so that because you are serving, you have to serve more users. So there is another question, but the co-channel user ratio remains the same. Okay, yeah, that depends on how big your size is. It's a very, very intelligent answer from Joseph. That of course, if you're not reducing the cell size, your D/R ratio remains the same. Okay. And if you're not using your n, what is the value of n you're keeping here? N is equal to 4 or 7 or what? Okay, very good. Let's move forward to the next slide. Now let's move to a little more advanced topic. Now in 4G LTE networks, or even WiMAX, 4G WiMAX networks, or any standards are coming up. These are the most predominant standards right now used for 4G wireless networks. Now there the demands are even higher. The people want to do video downloads on their smartphones, and they want excellent signal quality and all this stuff. So we have to make a radical change here, because the conventional 2G, 3G antenna techniques don't work for that high user bandwidth. So we use flexible spectrum reuse techniques. There are two ways of doing it: fractional frequency reuse (FFR) or a soft frequency reuse (SFR). So here we classify users into 2 categories. One is cell center users, the users which are closer to the base station, closer to the antenna, and the other is the cell edge users, which are lying at the edge, because it's considered the signal in conventional cell configuration. The user at the edge of the cell will have a weaker signal, and they will have poor quality of signal. And we use the user info like position information and a channel quality indication (CQI) to determine where the user is physically located and what type of signal he is receiving. Is he receiving a strong signal or a weak signal? And based on that, we divide them into cell center user or a cell edge user. Okay, there's a question: near far effect, right? Well, no, this is not the near far effect we discussed earlier. This is definitely in the far field, because we don't do wireless communication within the near field. Near field we use only for measurements in one scenario which I described earlier, just to do antenna measurements. This is not used for digital communication. Any mobile user must be outside the near field. Okay, so this is entirely different. Here it's only based on signal strength, signal to interference and noise ratio (SINR), which determines the boundary of the cell center region and the cell edge region, that where the signal falls below the threshold where the users cannot get acceptable quality. Okay, and it could be dependent on from carrier to carrier. There's no absolute parameter here. Like it depends on what are the user expectations from a service and what is the expected service that the carrier is providing. Based on that, they will categorize the users. The objective here is to provide excellent service to all the served users. Okay, let's move to the next one. Before we move, let's have a little question here. So which one you think it's true? You can type your answer in the chat box. So cell sectoring adds to wireless system capacity. Cellular base station transmitters high power and the cover range may extend to 100 miles. With FRF of 1, there is additional challenge of co-channel interference. Okay, very good. Some answers are coming. 1 is right. 3 is right. Yeah, base stations do not cover up to 100 miles. It's only that the TV transmitters and radio transmitters which might go to that type of coverage, but cell base stations have a much lower range, maybe few miles only, 6 miles, 8 miles, 5 miles, like that. Okay, very good, excellent. Let's move on to the next topic and see how the FFR. Okay, somebody asked a question, why 3? Let me go back to the slide. Yeah, so why 3? Because if we have frequency reuse factor of 1, that means we are keeping n equal 1. That means there is additional challenge of co-channel interference. That means every cell will have the full frequency spectrum allocated. So each adjacent cell will repeat that frequency. And you will have multiple signals coming from different base stations. And that will cause co-channel interference. I hope I answered your question. Yeah, if we use n equal to 1, we'll have co-channel interference because we are repeating a frequency in the adjacent cells. Okay, very good. Now, next slide here. Now let's see how we use fractional frequency reuse or FFR. So here, what we do, we split the spectrum into 2 bands, an inner or center band which has limited power and FRF equal to 1. What that means, that the cell center users, you have full frequency reuse. Full spectrum is available for cell center users. And then you have outer or edge band which has full power. That means we boost the signal power for the user served in the cell edge region. But here we don't have FRF equal to 1. It's like 2/3. So rest of the spectrum is shared with adjacent cells. This is the how we allocate the subcarriers. We allocate subcarriers at the time of network deployment. So it's a fixed scheme. Like when we deploy it, we just fix, okay, this is the frequency spectrum assigned to cell center users with limited power and cell edge users which have 2/3 of the spectrum, but the 1/3 is shared with the adjacent cell. This is one way of doing it. But more preferred way of doing it for the LTE and other networks, which has evolved over the last few years, is the soft frequency reuse. So in soft frequency reuse, what happens? We allow full spectrum reuse in each cell. Here you see FRF is equal to 1 for full cell. You have cell center users with limited power and cell edge users with full power. So you divide the frequency spectrum into major subcarriers. And that has higher power and used by all cell users, center and edge, and it is orthogonal in adjacent cells. Now, here the word orthogonal is important. Orthogonal means that the adjacent cells have a different frequency allocated for those users. Now, remember in LTE, if some of you are exposed to LTE, how the frequency spectrum looks like for LTE and WiMAX. Okay, and when we use OFDM, orthogonal frequency division multiplexing, you have up to 1024 subcarriers which can be assigned to the users. So users are dynamically assigned those frequencies which are orthogonal, which are different from the adjacent cells. So there is a question here, can you explain how antennas could control power in such a way? Well yes, you could control power to antennas based on, you need to have multiple antennas here, right? So if you are serving cell center users, you have different antennas serving the cell center users and different antennas at a different height on the same tower which serve the cell edge users. You might have seen on the cell towers the antennas are at different height. So that's the primary purpose of that. The lower height antennas are meant for the cell center users, and the more height you have, they are meant to serve the cell edge users. So you have to do a physical separation in that case, and each antenna power can be controlled separately. Okay, so you have minor subcarriers which have lower power and used only by cell center users. And power ratio is defined as the ratio of transmit powers of major and minor subcarriers. Now SFR-A is the one which is recommended for 4G LTE networks, and it has higher spectral efficiency compared to FFR. So this is the technique of choice. You have, what is spectral efficiency? You get more bits per second per hertz of the spectrum. You know here the frequency spectrum is a very expensive resource. So everything is with respect to that. Your spectral efficiency has to improve with this technique. So SFR helps you do that. It gives you more bits per second per hertz of our frequency spectrum. Okay, let's move on to the next slide. Now, femtocells. Now, some of you might have heard of it, how we use femtocells in 4G LTE. Now, and why do we need small cells or femtocells? Now, in urban areas or metropolitan areas in any major city, the signal coverage inside the buildings is not good. There are so many tall buildings, skyscrapers, which will reflect the signal in all directions, and you get blind spots if you have ever been with a cell phone in a metropolitan or a downtown area of a major city. So this problem has existed so far, like in 2G networks and 3G networks too. You lose your signal, your signal fades, and you have to go out of the building sometimes to make a call. Now what happens, the small or femtocells in 4G LTE, they are going to change this situation. They are supposed to be small, very small cells, just like a Wi-Fi network, something similar, which coverage might be between 10 and 200 meters, and which could be installed inside the building too. Essentially, they are low power base stations which could be installed anywhere in your home, in the building, or just hung on the wall somewhere, or hung on a pole. You don't need a cell tower to do that because their range is limited, their power is limited, and they serve a local region of users. Now, in case of LTE networks, and even in WiMAX they have suggested the scheme, but now LTE is more deployed around the world. You have an overlay network of conventional macro cells. Now you see, you have cell towers already installed. You're not going to uproot all the cell towers. They are already providing coverage to outside regions, to suburban areas, to villages and the countryside. The problem is with the downtown side, where you have metropolitan place in a city. How do you provide more coverage or better coverage in that area? You overlay the network of conventional macro cells with femtocells. So inside the picture you see in the cell, there is a macro cell center. There you see small circles inside, they are the femtocells. They are smaller base stations serving the local users. And then in the cell edge too, you could have outer femtocells. So this is a scheme with the femtocells. You provide an overlay network. So it's also called a heteronet or HETnet, a HETnet of macro cells and femtocells, serving all the users. Whether you are inside the building or outside the building or away in the countryside, everyone is covered with the best quality signal you can have for a 4G wireless network. Now here, these are centrally controlled by the mobile operator. The frequency allocation to each femtocell and to the macro cell is controlled by the mobile operator. Now we'll see. Okay, we'll see in the next slide how we actually implement that. Okay, so now there's a question here. Are you also increasing the total supplied bandwidth? Well, here we are not. We are not supplying the total bandwidth. The frequency spectrum is the same. We are just different way of implementing it. Now, wait for the next slide. We'll go to a little more detail in that. Okay, so this helps us add capacity in dense urban areas, provides coverage inside the buildings, and higher spectral efficiency. BPS per hertz will be very high because we are serving so many users within the same spectrum. If we add spectrum, then our spectral efficiency will fall down. So see, the idea is that we are not buying more spectrum. We are just adding more users within the same spectrum. Well, wait for MIMO to come in. We'll talk about that too. Okay, so let's see what are the issues involved here when we do. Okay, now you see the picture here, how the co-channel interference manifests in this case. You have a macro base station with a tall cell tower which is sending signals all around. And then within that covered area, you also have a femto base station which is also sending signals. So let's say there is a femto user, I see a laptop there inside the building, which is receiving a strong signal from the femto base station, but an interference signal from the cell tower, the same frequency, or maybe orthogonal frequency, is coming from the cell tower. This could cause co-channel interference if you have the same frequency coming in over there from there. Now there's a macro user, which is a smartphone, which is moving around moving around between the urban area and the suburban area and the countryside. Now this user also could receive an interference signal you are receiving two signals, one from the cell tower and one from the femto base station, if they are at the same frequency. So this is the co-channel interference that might manifest if we have an overlay network of a macro cell and small cells or femto cells. So how do we alleviate the situation? We use orthogonal frequencies. With OFDM frequency schemes, we can do that. We assign orthogonal frequencies or non-overlapping frequencies to femto cells and the macro cell region to mitigate co-channel interference. Now, this is one reason why the mobile operator has to control the frequency allocation to the base stations in the macro cell as well as in the femto cell. So it has to coordinate all that allocation of frequencies so that there is no co-channel interference. When you are inside the macro cell center, your frequencies will be different from when you use a femto cell inside the same region. That's why they are shown in different colors. All these different regions, they have allocation of different frequencies within the same frequency spectrum that you are allocated. We are not adding supplied bandwidth. The supplied bandwidth remain the same. That has been auctioned to us by some government organization. In US, it's the FCC, Federal Communication Commission. I think in India, it's a different organization. In Europe, there's a different one. Each country, they have their own regulation. So they have already sold you the frequency spectrum. Now you have invested the money in that. Now you don't want to buy more frequency spectrum. You just want to devise intelligent ways how to use it to the maximum possible extent. How to serve more and more users within the same frequency. And this is one way of doing it. You build an overlay network of macro cells with femto cells inside and dynamically control how you allocate frequency from within the spectrum to each of these users so that they do not have any co-channel interference. Okay, let's move on to the next one. I think today's webinar is taking a little more time. Please bear with me. It's because we have so many topics to cover. Okay, let's see which of the following statements are true. LTE femto cells are not controlled by mobile carriers. Macro cells form overlay network or HETnet with femto cells. Macro cells and femto cells are assigned orthogonal frequencies to overcome CCI. Wireless LAN is an example of femto cell not controlled by mobile carrier. So take a moment and write the answer, which one you think is true. Well, LTE femto cells are not controlled by a mobile carrier. Macro cells form overlay network or HETnet with femto cells. Yes, that is true. Macro cells and femto cells are assigned orthogonal frequencies to overcome CCI. Yes, that is true. We just talked about that. Wireless LAN is an example of femto cell not controlled by a mobile carrier. Now, what about this, number 4? Yes, that is true too. Well, wireless LANs are independent wireless networks, which are not controlled by anything, right? At your home, if you have a Wi-Fi router, it's only you are the user. And it's your responsibility to make it sure that you don't have interference with your neighbor. What you do, if your neighbor is using the same channel, you change your own channel. If somebody is using channel 8, you switch to channel 9 so that there's no co-channel interference. Some of you who have used these wireless LANs in your homes or businesses or enterprises might have noticed that. You always have to make sure that you're not using the same frequency as what your neighbor is using. Otherwise, you simply cannot receive any signal, any data from your wireless LAN. But they are not controlled by any mobile carrier. It's